Here we have another pretty difficult example just because we do have a fraction and then we also have this ln of x. So I'm going to remind myself of rule 9. The derivative of the natural log of x, what was it? Do you remember from test 1? You get to cover up the ln, you do the derivative of the inside over the original inside x, and the derivative of the inside is 1. Or you can just memorize the derivative of the natural log of x is 1 over x. Otherwise, derivative of the inside over the original inside works as well. And now we're ready to actually take the derivative. I don't have anything to rewrite that's in the denominator. So I'm going to take the derivative of the natural log of x first, which is 1 over x. Then this next piece, I'm going to bring down the 5. 5 times 1 over 20 is going to give me a 5 over 20, which will reduce to be 1 over 4 x to the fourth. I need to take the derivative of this, but I see I've made a fraction and I don't want to use the quotient rule. So I'm going to need to rewrite this because I've made a fraction. So I'm going to take a step before I take the next derivative. I'm going to rewrite this as x to the negative 1. Negative because it was in the denominator, 1 because it was just to the first power. And then I have 1/4 x to the fourth, which I don't want to take the derivative of when I'm just rewriting for that step. I'm finding the fourth derivative, so I'm definitely not done yet. I'm ready for the second derivative though. I'm going to take the derivative of x to the negative 1, which is going to be negative 1 x to the negative 2 when I bring down the power and subtract 1 for the new power. I'm going to bring down this 4 as well. 4 times 1/4 is going to just be 1 x to the third. So hey, the derivatives are kind of getting nicer as we go. Sometimes that happens with higher order derivatives. We're going to bring down the power again. Negative 1 times a negative 2 is going to be, two negatives are going to be a positive 2x to the negative 3. Derivative of x to the 3 is going to be 3x to the 2. I'm asked for the fourth derivative, so one last one to do. And we do a 4 in superscript up high. Bring down the power. 2 times negative 3 is negative 6. X to the negative 4. And then 3 times 2 is going to give me 6x for that last part of the derivative. And there's our final answer for that one. And we're going to do the same thing on the next one. I would definitely feel free to pause the video. It's very similar to the one we just did. It's actually just a slightly easier version of what we just did, just to see if you can try it on your own. So try to take the third derivative of 2 over x squared. I'm going to do it here as well. If you can't get it on your own, I'm going to first just rewrite the function. It's 2x to the negative 2. And I'm finding the third derivative. So my first derivative, f prime of x, bring down the power, is going to be negative 4. X to the negative 2 minus 1 is negative 3. Second derivative, bring down the power. Negative 4 times negative 3 is going to make it a positive 12. X to the negative 3 minus 1 is negative 4. Lastly, my third derivative, and then I get to stop. 12 times negative 4 is negative 48. X to the negative 5. The only other way that this could be written, because sometimes these are multiple choice, so just to show you the other way it could be written in case it's a multiple choice question, I could keep the negative 48 on top and put that x to the negative 5 in the denominator as positive where it belongs. So either answer is fine. I would not simplify at all unless it was a multiple choice and you just had to pick the simplified answer. Otherwise, I would have left it as just negative 48 x to negative 5, just so I don't have to worry about rewriting wrong. So our last example of just finding a higher order derivative, we have d squared of 4/3 pi r squared over dr squared. Let's figure out again what this means. This is doing one of those definitions that we talked about earlier. D squared means second derivative. Second derivative. And dr squared is with respect to r. We showed you dy dx means the derivative of y with respect to x. This is d, and it has an r in it, so it's with respect to r. So this notation is kind of confusing. This is probably the hardest part, but we're going to need it for implicit differentiation, so I'm going to use it just this once as like a preview, and there's one like this in the homework. Don't let the r's throw you off. So I'm going to label them in words on the side as well, just because the notation is difficult. So the first derivative would just be d over dr, the derivative of 4/3 pi r squared with respect to r once, just the first derivative. I would just bring down the power and subtract 1 for the new power. Bring down the power. It's a fraction, so I'll do it in a couple steps. I have 4/3, and then I bring down the power 2, and pi is a constant as well, so I'm going to keep the pi, and raise r to the 2 minus 1 is just to the first. And that's where I'd go and grab my calculator, and 4/3 times 2 is going to give me 8/3 pi. Never multiply out by that pi just because it's going to give you this crazy decimal that doesn't stop. Here's my first derivative, 8/3 pi r. I can multiply the 4/3 times 2, just don't multiply out that pi or else you're going to get a crazy decimal and WebAssign is going to mark you wrong because you'll have to round. You can't type in all those decimal places. My second derivative using this notation would be d squared. I'm going to take the derivative twice of 4/3 pi r squared with respect to r twice. Which means I'm going to take the derivative of my derivative. I need to take the derivative of 8/3 pi r. So the derivative of 2r would be 2, derivative of 16r would be 16, derivative of pi r would be pi, so the derivative of 8/3 pi r is just 8/3 pi, our mini rule, but with r's instead of x's. So don't let that one throw you off in the homework, and if it does, just send me an email. But it's some crazy notation, and it has r's in it, and it's still just a higher order derivative, totally doable, and there's all of really the hardest examples I could think of for higher order derivatives to show you guys, and now you can try the ones on the homework that just ask for the derivative multiple times.